Good evening. Do you have any doubt from last class?
No, sir.
We have done till this part about bulk modulus. We are doing stress strain, mechanical produced solids. Suppose in this question, suppose there is a vessel in which liquid is completely filled and there is a piston on surface on which a block having mass m is placed. Now suppose if a body having radius r is inserted in it. So you'll be asked, find fractional change in radius of sphere if bulk modulus is beta. Let's say area of this particular piston is A. Try to solve.
Okay, sir.
First, tell me about the idea, how you'll approach this problem. If I just 1 minute. Let me give you some idea how to approach this problem. Since you have to calculate fractional change in radius. So first thing, how radius will depend upon volume. So we may write volume equals to 4 by 3 times pi r cube related to this spherical body. So if you calculate fractional change in volume according to the error method, it will be delta V divided by V. 4 by 3 pi is a constant term, so we just neglect it. We have r to the power 3, so it will be 3 times of delta r by r. So put delta V by V by this, or replace delta V by V as 3 times delta R by R. Now, the next thing is this block having mass M is placed over this particular piston having area of cross section A. So there would be a force acting on this plate due to this block, which is mg. So pressure exerted will be equals to force over area of cross section. Force is mg divided by area of cross section. Now we have pressure and we have delta V by V. So according to the formula of bulk modulus, just put all the values and try to find delta R by R. Ifra,
Okay.
is it clear?
Yes, sir.
Okay. Good. So as we have beta equals to pressure divided by delta V by V, so we can write pressure is mg by A. Delta V by V is 3 times delta R by R. So move this delta R by R towards left side. So you get delta R by R equals to mg by 3 times of beta into A. Okay. So this is all about stress strain related to different types. Next is there will be some subjective question related to this part. You'll be asked to define which one is more elastic. Suppose rubber and steel. So you have to define it mathematically. So let me define you how you'll approach this problem. So you'll be asked which is more elastic. First, in steel and rubber. Second example will be water and gas. So for any pair, first, let's say for steel and rubber.
So steel is more elastic.
How you can define it?
Sir, I
Mathematically?
don't know. I don't know mathematically, but more elasticity means we have to put more efforts to change its configuration.
Okay. It also means it have greater value of or larger value of modulus of
Yes.
velocity. So it
Yes.
will have tendency to attain exactly the same configuration on removal of deforming force. So let's say there is support from which a rubber having length and area of cross section L and A, and another steel having same dimension is attached. So this is rubber and this is steel. Now suppose if you apply same deforming force on both of them, let's say if same deforming force is applied on this part as well as this part. So which one do you think will have more deformation or more elongation?
So rubber will have more elongation.
Good. So amount of deformation produced in rubber would be more. Let's say it will be to this part. So this is delta L, and steel, it will be very small. Let's say it will be till this part. So you'll say for same dimension of rubber and steel on applying same load or force, delta L in rubber will be more as compared to delta L in steel. Is it clear?
Yes, sir.
And next, since modulus of velocity, or in this part, since it is extending long length, we can define Young's modulus. So according to the relation, y equals to f times L divided by a times delta L. Or you can write delta L is inversely proportional to Young's modulus. So we have delta L for rubber greater as compared to delta L for steel. Therefore, Young's modulus of steel will be greater as compared to Young's modulus of rubber. Hence, the substance which having more modulus of velocity will be more elastic. So, steel will be more elastic. Is it clear?
Yes, sir.
So this is the way how to prove or mathematically define the elastic behavior of particular substance. Similarly, for water and gas, you may say, take equal volume of water and gas in a balloon and then apply same pressure on both of them. So you'll get more amount of change in volume in gas as compared to water. So it means delta V is more for gas as compared to water. So water will have more modulus of velocity, that is bulk modulus. It means water will be more elastic as compared to gas. Is it clear?
Yes, sir.
Okay, just write it down.
Done, sir.
Okay. The next term in this chapter is stress strain curve. Suppose from any support, a wire is hanged, and we have to define some property of it on applying some deforming force. So initially, if you apply some deforming force, let's say from this point to this point, or a stretched wire up to small displacement, let's say from this point to this point, O to E. So at this instant, if you remove that deforming force, then this body will have exactly the tendency to acquire initial state exactly. So on removal of deforming force, it will tend to go back to exact original configuration, let's say 2.0. Now, suppose if you extend this wire a little bit more, let's say from this point to this point B. And then if you remove deforming force, then it will have still the property of elasticity, or to regain back its original shape on removal of deforming force, but now with some amount of permanent deformation with it. So on returning back, it will reach to this point. So there will be permanent deformation from this point to this point, which is called permanent set. And that will be about 1 to 2% of its total length. Is it clear?
Yes, sir.
Let me define it once more. Since initially, if you apply stress to this particular object up to certain extension, let's say 2.A, and then if you remove the deforming force, then at this instant, object will return back exactly to its own state as it was initially, that is at point O. Now, suppose if you extend it a little bit more beyond A, let's say to this point B, then still object have ability to get back to acquire its original state. That is, it have ability to regain its original shape. But now it having some permanent deformation with it, which is called permanent set. And that will be about 1 to 2% of its actual length. Up to this part or up to this length, object has elastic behavior. But now if you further stretch it a little bit more, it will move along this path. And then if you remove deforming force in this entire region, then object will remain in its own condition, own state at this instant. Means object has lost their property of elasticity in this particular region. So this region is called plastic region. Is it clear?
Yes, sir.
And the body has elastic behavior from 0 to B. So this point B is called yield point. The last point up to which object having elastic behavior is called yield point. Now, if you stretch it from B to C, so C is the point up to which body has ability to withhold maximum amount of stress on it. So it is called ultimate stress. But now, if you further apply deforming force to stretch it a little bit more, then it will start flowing like this. And at any point D, it will get broken up. So from C to D is the state of flow of that body, and point D is called breaking point. Is it clear? This entire
Yes.
curve. So
Yes.
this vertical line is basically amount of stress applied to it, and this horizontal line is basically amount of deformation produced in it, that is strain. Since in this part we are applying force or stress to elongate it, so you'll say it is tensile stress. There will be similar curve if you apply compressive stress to this particular body. So it may go along same way like this to reach at this point. Is it clear?
Yes, sir.
Okay, first draw this entire part, then I will define you each term.
Done, sir.
First, from O to A. If deforming force is removed, then object will acquire exact original shape. So up to this region, Hooke's law will be valid. So Hooke's law is valid up to this region. Next is from point A to B. If you remove deforming force, so if deforming force is removed, then object will still have tend to acquire its original shape, but with some permanent deformation with it. That is called permanent set. Next is from B to C. If deforming force is removed, object will no longer tend to return to its original state. That is, lost their ability of elasticity and have acquired plastic behavior. Next is C to D. Without applying stress, object will themselves start to flow and get broken at any contradiction. So the shape at this point of body will be like this. So at any contradiction, let's say at this point, it will get broken. Is it clear, Ifra?
Yes, sir. Yes, sir.
Okay, just write it down.
Done, sir.
You have learned thermodynamics in chemistry?
Sir, in coaching, states of matter is going on.
Okay. Now, related to this curve, there will be two different questions. First, the elastic behavior of a substance. So as I defined you in the previous class, slope of stress sustained curve defines your modulus of elasticity and which defines the elastic behavior of body. So first we can calculate slope of this particular graph. So E will be slope of stress strain curve and will define the elastic behavior of body. Next, for this graph, we may define some property of metal or some other substance. First is called ductility. Second is malleability. And third is brittle nature. You must have learned these three terms in class 10th in chapter metal and non-metal. Do you have any idea?
Yes, so ductility is when we draw metal into wires, and malleability when we draw it into sheets, and brittle nature is shown by non-metals which break down when pressure is applied on it.
Good. So ductility is basically the property of material to be drawn into thin wires. To be drawn into thin wires. Malleability is to be drawn into thin sheets, and brittle is to be broken into fragments. On applying pressure or force. So these property of material depend upon plastic nature of that particular substance. So ductility and malleability is directly proportional to plastic region of that particular substance. Greater the plastic region of that metal, it will have greater property of ductility and malleability. And next, for brittle substance, inversely proportional to plastic region. So if plastic region is small, then it will have greater possibility of brittleness as compared to ductility and malleability. So on knowing the length of plastic region, we can define these three terms. Is it clear?
Yes, sir.
Okay, just write it down.
Done, sir.
So the question on this particular term will be, suppose you have a curve let's say this substance is A, substance is B. This is stress and this is corresponding strain. So related to the curve, you have to define which is more elastic, brittle, ductile. Try to answer.
So elastic is A and brittle also A and ductile B.
Good. As we know, elasticity depends upon slope of a stress-strain curve till it obeys Hooke's law. So till it at this point and at this point. So slope of A is greater as compared to B. It means A is more elastic as compared to B. For brittle nature, we may just compare the length of plastic region. So it will be from this point to this point only for A, and it will be from this point to this point for B. So A having smaller length of plastic region, so it will be more brittle, and B having larger length of plastic region, so it will be more ductile or more malleable. Okay, good. You have written till this part?
Yes, sir.
Okay. So this is all about the first part of this elastic behavior. Next is potential energy stored in a wire. Suppose there is a support from which a wire is hanged vertically. Having length L and area of cross section A. Consider a wire is hanged vertically. Now, if you apply any deforming force, let's say along this direction, to deform it, so the deformation in this particular wire will be like this. Let's say total deformation in this wire is up to this length. But this amount of deformation in this particular wire must have achieved in stepwise. So let's say in last part, it may have achieved this much amount of deformation, dy, and rest the term from this point to this point is y, so that total elongation from starting to this point is L. Is it clear?
Yes, sir.
So we can say for this deformation dy, we must have to apply some amount of work over it to stretch it further by dy. So just 1 minute. According to the relation, Young's mod is equals to force times length by A times deformation. Let's say we have deformation till y. So we can relate force equals to y into A divided by L into small y. If you apply this particular amount of force to this wire to stretch it further by dy, so you must have to apply some amount of work done. So let's say W amount of work is done to stretch wire by dy. So work done equals to force times displacement. We have force as YA divided by L, y times dy. Now integrate both sides. In right hand side, we have y as a variable, so its length or its initial limit will be 0 and final limit will be L, the maximum elongation produced in this wire. dW, or the amount of work done on this wire to stretch it a little bit more by dy, will convert into potential energy U. So it will be y times A divided by L. We have y to the power 1 in this part. So according to the rule of integration, y to the power 1 will be y to the power 1 plus 1 divided by 1 plus 1. So you will get y squared by 2, limit from 0 to L. Now put the value of upper limit and lower limit. You will get YA times L squared by 2. Is it clear?
Yes, sir.
Okay, just write it down to this part.
Done, sir.
Now we can transform this formula in terms of force and extension as U equals to half YA divided by L times L to one part and L to the other part. In this part, if you see, Y is just comparable to L. So we can write force equals to YA divided by L times Y, equivalent as YA times small l by capital L. Is it clear?
Yes, sir.
So we can write this part as force and this part as elongation. So it will be half times F into L. So it will be half times force times extension produced in this wire. Now we can further transform this formula in terms of stress and strain. U equals to half force times extension. So if we divide it by volume and multiply it by volume, it means if you multiply and divide by same term to any fraction, then there will be no change. So we can further expand it as 4 times expansion Divide by volume is area into length of the wire times volume. This part is nothing but force per unit area. So it will be termed as stress. This part is nothing but deformed shape by original shape. So we can write it as strain. So this will be equivalent of half times stress into strain times volume. Is it clear?
Yes, sir.
Okay, just write down.
Done, sir.
Now related to potential energy, let me give you a question. A wire having Young's modulus as 2 into 10 to the power 11 Newton per meter square. Dimension of wire is 4 mm cross 2 meter. Find stress and potential energy stored. Just 1 minute. There should be some deforming force. Okay, try to solve. 10 to the power 4 Newton. 4 into 10 to the power 4 Newton. Ifra, any problem while solving?
No, so just sending answer 1 minute.
Ifra, you have done a little mistake. We have force as 4 into 10 to the power 4 and area of cross section is 4 mm square. So stress will be amount of force applied divided by area of cross section. So it will be just 10 to the power 10 Newton per meter square. Okay, Fra?
Yes, sir.
Okay, try to find potential energy. Shra, you have solved the second part?
Yes, sir.
Okay, just one minute. According to the formula, potential energy equals to half times stress times strain times volume. We don't have strain, so we can write Young's modulus equals to stress divided by strain. So strain from this part will be stress divided by Young's modulus. So it will be half stress times stress divided by Young's modulus times volume. So it will be half times square of stress. So it will be 10 to the power 10 square. Volume, area of cross section is 4 mm. So it will be 10 to the power minus 6 times length 2 divided by Young's modulus 2 into 10 to the power 11. So this 2 and this 2 will cancel out. This 2 and this 4 will cancel out in 2 times. So you're left with 2 into 10 to the power 10 to 20 minus 6, 14 and minus 11. So it will be 3 joule. Good. You have done like this? Or you
Yes,
have
sir.
first calculated strain and then put the value of the strain in this part?
So first I have calculated the value of strain.
Okay, okay. Now the next problem will be relation of this particular elongation with spring-like behavior. As a rod behaves like spring due to its intermolecular interaction or due to its elastic behavior. Suppose you have a spring having this much amount of length. So if you apply a force on this part along this direction to deform it, so F external will be K times X, where K is called force constant or spring constant. Similarly, for a rod having length L, if you apply deforming force along this direction, so according to the rule or relation, Young's modulus equals to F times L divided by A times delta L, or just say it as like this. So we can write F equals to YA divided by L times small a. So just compare these two equations. So we can write spring constant equals to YA divided by L. Is it clear?
Yes, sir.
So you may be asked sometimes to find the spring constant related to any problem. So spring constant related to solid would be equals to Y times A divided by L. And we can use this formula in chapter oscillation waves to define spring constant or factor affecting spring constant by cutting it or by stretching it and so on. Okay.
Okay, sir.
Next is if you hang a wire or a rod freely from any rigid support, will there be any elongation in it due to its own weight?
Yes, sir. There may be elongation due to its own weight.
Why so?
So because force of gravity is acting on
Okay. Suppose you have a wire having length L. So at any instant, you will say there will be some portion of length. Suppose I'm considering this much amount of portion of length, dy. And the amount of length of wire from this point to this point in downward direction, let's say y. So this much amount of length would have some amount of weight with it. So it must be attracted by gravity along downward direction, and that must be applying some tension to the segment of wire to elongate it. So you'll say at any instant, there will be some segment of wire below it, which must be applying some tension to the above portion, due to which there will be some elongation in this wire due to its own weight. So elongation in a wire due to its own weight. So it will be just half of F times L divided by A times Y. Is it clear?
Yes, sir.
Okay, just write it down. I'm coming just 1 minute.
Okay, sir.
Okay, you have written to this part?
Yes, sir.
Now the next term in this part will be elastomer. Do you have any idea about this? What do you mean by elastomer?
No, sir.
You must have used thermocol and rubber band both.
Yes, sir.
What will be the main use of thermocol according to you?
So the things which are made up of glass, it protects them from cracking when they fall.
Good.
Nothing.
So you can say, if you compress thermocol a little bit and release it, then it will have tendency to acquire exactly to its own position or own shape. But if you compress it a little bit more, it will be fractured or broken up. It means the substance which having only elastic behavior and there is no plasticity, so it behaves like, if you apply a stress to that body, so it may obey this graph like this. So here is stress applied to that body and there is corresponding strain to it. So if you apply stress to that body, so it may reach to this maximum point that is called saturation point. And if you further apply more stress to it, it will get broken up. So this is the last point up to which it can be extended. Now, if you release the deforming force at this point, then it may acquire its original shape, but in some other manner. So while elongation, it will follow this path, and while compression, it will follow this path. So you can say there is some difference in proportionality while elongation and while compression. Suppose if you draw a horizontal line to this point, it means by elongation, strain will be this point, and while compression, it will be at this point. Is it clear? So we can say stress and strain is not directly proportional while elongation and while compression. Is it clear?
Yes, sir.
So elastomers are the substance which having only elastic behavior. Beyond that, it will get broken up, and it will follow this type of graph. It means stress and strain is not directly proportional to each other while extending or stretching and while compressing back. So this type of relation, when there is some lagness with respect to one another in physics, is called as hysteresis. So you'll be asked to define what do you mean by hysteresis. So hysteresis means the property of one quantity lagging behind with respect to other one while elongation and while compression back. Is it clear?
Yes, sir.
So first, elastomer. The substance which has only elastic limit. Next is the lagging behind property of stress with respect to strain is called hysteresis. Or you can say it is mechanical hysteresis. So the area of this particular graph defines you the amount of energy lost during extension and compression. Or you can say elastomers are the substance which having shock absorbing property. So the greater the area of stress strain curve for that material, it will be good shock absorber. Is it clear?
Yes, sir.
So elastomer are shock absorbing material. Greater the area of stress strain curve, greater will be shock absorbing property. Okay, just write it down to this part.
Okay, sir. Done.
Last term of this chapter is Poisson's ratio. Suppose you have support and a body having length L is hanged. So if you apply deforming force on it, so it may deform or elongate like this, but with some contraction, as volume of object should be constant. So initially, we have length of the sphere from this point to this point. There is elongation from this point to this point as delta L. Correspondingly, diameter of the sphere from this point to this point is D. Now it becomes D minus delta D. So in this part, we have two different deformation. One is called longitudinal. So if you have to calculate amount of deformation produced in it, so it will be called as longitudinal strain. So it will be delta L divided by L. There is another deformation in this part, which is in terms of width, which is called lateral strain. So it will be delta D divided by D, or you may say delta R divided by R. Since width is decreasing, so change will be negative and this change will be negative. Now the ratio of these two deformations produced in this term is called Poisson's ratio. So Poisson's ratio equals to lateral strain divided by longitudinal strain. Poisson's ratio is denoted by sigma, so it will be delta D divided by D whole divided by delta L divided by L. And with some negative sign, or you can say delta R divided by R, delta L divided by L. Since it is the ratio of the same term, so you can say it is unitless quantity. Is it clear, Ifra?
Yes, sir.
Just write it down to this part.
Done, sir.
Now, there will be some one-word question related to this part to define the value of this Poisson's ratio, Young's modulus for different body. For a rigid body or perfectly rigid body, there will be no change in volume or dimension. Young's modulus, shear modulus, bulk modulus will be equals to infinity, but Poisson's ratio will be equals to 0.5. Next, in general, the value of Poisson's ratio lies in between 0.4 . So this is theoretical value of Poisson's ratio, and this is practically achieved. Is it clear?
Yes, sir.
So just remember this part only. Just write it down.
Okay, sir.
Ifra, you have written?
Yes, sir.
Okay, so this is all about this entire chapter, that is mechanical properties of solid.